This video is about strong induction, for when regular mathematical induction just won't do. Suppose we want to prove a proposition Pn for all positive integers n. Sometimes, instead of just using the previous case, pk, to prove the next one, pk plus 1, we have to reach back and use several previous cases, like pk and pk minus 1, and maybe pk minus 2, to prove pk plus 1. This is the sort of situation when we need the method of strong induction. To use the method of strong induction to prove a statement for all positive integers, we still do a base case and show that P of 1 is true, or sometimes it's useful to prove several base cases, like P of 1, P of 2, and P of 3. And then, for the inductive step, we prove the statement that if P is true for all the numbers, all the way from 1 up through k, then it's true for the next one, k plus 1. From the base case and the inductive step, we conclude that the proposition is true for all positive integers. The main difference between regular mathematical induction and strong induction is that for regular mathematical induction, we're just proving that pk implies pk plus 1. We just need the previous case to prove the next one. Whereas in strong mathematical induction, we show that if all the previous cases are true, the next one is, and we actually are going to be using several of these previous cases. Consider the sequence of numbers a1, a2, a3, and so on defined as follows. a1 is defined as 0, a2 is defined as 1, and for n bigger than or equal to 3, we define an as 2 times an minus 1 minus an minus 2. So each subsequent number is defined in terms of the previous two. Let's look for a minute at a few examples of these numbers. So a3 is going to be defined as 2 times a2 minus a1. Well, we can work out what that is because we know that a2 is 1 and a1 is 0. So this is equal to 2. a4 is 2 times a3 minus a2. Once again, we could work this out. 2 times 2 minus 1, which is 3. And if we keep working these numbers out, we might observe that each an is always 1 less than n. It's always n minus 1. So let's prove this observation. Since this is a statement about integers, it's natural to use induction. But since we have to reach back 2 steps, not just 1, to get our next number, it makes sense to use strong induction. For the base case, I'm going to actually do 2 base cases because I know that I may need to reach back and use both of them. So I'll say that when n equals 1, a1 equals 1 minus 1, which is 0. That works. And a2 is 2 minus 1, which is 1. So that works for n equals 2. Next, the inductive step. So we're going to fix k. Actually, I'm going to fix k bigger than or equal to 2 because the base cases get us up to n equals 2. And then we're going to assume that for all integers j in between 1 and k, all the way up through k, our proposition that we're trying to prove is true. That is, our aj equals j minus 1. This is our inductive hypothesis, that our proposition is true for j equals 1, 2, all the way up through k. And now we want to show that the proposition is true for k plus 1. That is, that a k plus 1 equals k plus 1 minus 1. That's our proposition with k plus 1 plugged in for n here and here. So this is what we're trying to show. All right, so let's use the information we have and our inductive hypothesis. The information we have as far as this recursive rule is that a k plus 1 equals 2 times a k minus a k minus 1. I got these indices here got all of the indices by plugging in k plus 1 for n. Here, k plus 1 minus 1 is k, and here, k plus 1 minus 2 is k minus 1. Now, by our inductive hypothesis, right here, we know that AK is K minus 1, and we know that AK minus 1 is K minus 1 minus 1, i.e. K minus 2. We know that it's true because we're assuming this proposition holds for all j between 1 and k. And we know that k is between 1 and k. And we also know that k minus 1 is between 1 and k. Notice that we're using the fact that we fixed a k bigger than or equal to 2 here, so that when we drop back to k minus 1, even if k were 2, k minus 1 would still be bigger than or equal to 1. So we're not going to drop off the edge of the sidewalk here when we reach back 2 because of where we started. Plugging this into our recursive rule, we get that k plus 1 is twice k minus 1 minus k minus 2. This simplifies to 2k minus 2 minus k plus 2, which is k. And that's exactly the same thing as k plus 1 minus 1. So we have that k plus 1 is k plus 1 minus 1, which is exactly our statement we have to prove for the case of n equals k plus 1. So this proves our inductive step, and therefore an equals n minus 1 for all n that are positive integers. This video gave an introduction and an example of strong induction. Often strong induction has several base cases, but the distinguishing feature of strong induction, if you want to think of the ladder analogy, is that we have to reach back several rungs in order to get to the next rung. Anytime you try regular induction and find yourself having to reach back further than just the previous step, that's a good hint that you may need strong induction.